Hi everybody, and welcome to the third video in the series TensorFlow Basics with Hemant. That's myself. In video 1 and 2 we got familiar with the tensors, constants, variables, eager execution, and also using gradient tape to trace operations, calculate gradients, and update weights. So that's a lot of ground we have covered. In this video, that is the third video in this series, we will explore a few questions around the concept of a model, layer, and a module, and try to find some answers for them. So some of the questions are, what is a model? What is a layer? What's the difference between the two? Why model and layer are needed in the first place, and how are model and layers created? And then how do we need to persist a model? So what's the need to persist a model once it is created? And once it is persisted, how can we load it back onto a different place? Maybe we trained a model on a Python server and we want to load it back onto a small factor device, right? And the last thing that we'll discuss into this particular session is what do we have to do to solve a given machine learning problem. So we'll discuss the different steps involved into the machine learning. Okay, so let's get started. So let's first see what is a model and a layer. So we saw in the first video that a training process is split into a forward pass and a backward pass. So in a forward pass, what we do is we input the tensors and a computation is done on the tensors, and a computation can consist of a series of operations, right? So in short, model and layer both encapsulates the trainable variables and the computation graph. Okay, so before we really discuss about the concept too much, let's take a look at the code snippets, two code snippets that we have on the screen. So the first code snippet represents a layer and the second code snippet represents a model here. Okay, so let's compare these two. So if you see here, both of them, they basically are inheriting, or we are subclassing these two classes from tf.module. So here we are subclassing tf.module, here also we are subclassing tf.module, right? And both of them, they have these two methods, definite, def call. So here also we are definite and def call. Okay. Now what we are doing in the init in the this class dense, which is representing a layer. So what is being done here is we are creating two variables, tf.variables. One is a w and another is a b. So w is weights and b is biases, and we are basically giving it a shape, like the shape like an input feature and output feature, and we are giving it a name as well. And then there is an operation on it, which is a matrix multiplication. So we multiply the input by the weight and add a bias to it, and then we run that output through an activation layer and we return that. In the sequential module, what we are doing is, in the init method, what we are doing is we are creating two instances of this layer, right? So dense 1, dense 2, we are creating two instances, and while creating two instances we are giving the input features as 3, output features as 3 here, and in this case it is 3 by 2. So what we are doing here in essence is actually we are creating two different layers with different sizes of input and output features. Okay. And then in the call method, so here we had done a matrix multiplication of input of weight and added bias to it. In this particular case, what we are doing is we are instantiating a layer itself. So we are instantiating a layer 1 here, and we are giving it an input x, and then this output which is generated by the first layer, that is fed into the second layer, and that is what is being written. So what does it mean? The calculation in this particular case is actually we are giving an input through a series of layers here, and then final output is something that we are returning here. Okay, and in order to conduct this calculation using a module, what we are doing is actually we are instantiating the sequential module. right? And we are giving it a name, the model. And then once it is instantiated, we are giving it an input, which is tf constant 2 into 2 into 2, 2 comma 2 comma t 2. So this is a tensor of the size of 1 by 3. So if you see here, now the first layer, okay, it is 3 by 3. So if we are multiplying, if we are doing the matrix multiplication here for 3 by 3 weight matrix with 1 by 3, what we are going to get? 1 by 3. Okay, and then that 1 by 3 is fed into the second dense layer, which is 3 by 2. So finally we get 1 by 2 size vector as an output. Okay, and when we get to the notebook which will actually run this code, we will be able to see the final output also here, right? So if we now consider these two code snippets, if we think of it this way, actually model represents a complete artificial neural network. Now since artificial neural network can consist of different type of layers, that is input layer, hidden layer, output layer, and so on, it is helpful to encapsulate a specific type of computation and associated weights to a layer as a layer, so that we can reuse a layer while building any model. So in this particular case, we created a dense layer to represent a particular calculation here. Okay, and then we are instantiating it again and again, right? So we are reusing this layer to create a computation, right? But obviously instead of this dense, we can have different type of layers. So for example, if we are doing an image classification, we can use layers like convolution layers. If we are trying to predict a sentence, predict the next word into the sentence, we can use something like an RNN or an LSTM layer. So essentially the layers are encapsulating specific type of the calculation or an operation. And then when we are talking of a model, what we are doing is actually we are constructing a series of layers so that we can create a more complex computation out of the specific computations which are provided into the layers. Okay. Now in the earlier slide, what we saw was the input which was given to this particular layer. So when we are trying to create this particular layer, this is hard-coded, right? The input features are hard-coded. That means we need to know the input features in advance, right? So if we want to quickly improve on that concept, we can create something like this. We can create a flexible dense module. So this is subclassing the tf dot module. Now we are creating the same weight and the biases here, but what we are doing here is actually when we are creating this weight variable, what we are doing is we are taking the x dot shape -1. That means the last dimension of the input we are going to take as the dimension for the weights, right? And the output features will remain the same. So for example, in the last case we had a 1 by 3 input, right? So what is going to be done here is it is going to take the last dimension of 1 by 3, so that will be 3. So this will be 3 by whatever is the output feature, right? So that's the concept of a little bit of a flexibility. So when we instantiate a layer, whatever is the shape of the input, we will be able to create a layer out of it. That is the concept here. Okay. Now another concept is module. If we are assigning any kind of a TF variable, or if you are assigning any kind of module to the property of the TF dot module, then it is automatically collected. Okay, so why this is helpful? Because if you are able to automatically collect all the variables, then it becomes very easy to save and load the variables. Okay, so and it does it recursively as well. So if there is a module and within the module there are other variables, they also are going to be collected automatically. Okay, so how can we access the collected variables? So if we are creating an instance of the tf.module, say in this particular case it is named as simple underscore module, then we can access it using the dot trainable variable. Okay, or if we just say dot variables, then we will get all the variables whether they are trainable or non-trainable, and we can also collect the submodules. Okay, so if we have an instance of the tf.module and if we say dot submodules, we'll get all the submodules of that particular module. Okay, and we'll see all these concepts in the notebook also when we are executing. We can also get the values of all the variables, list of all the variables, by iterating through it. So if we say my model dot variables and then we iterate it using the for loop, we'll be able to print all the variables into that particular model, right? Now we had mentioned that it is helpful to collect the variables so that we are able to save and restore the variables, right? So let us imagine two different scenarios why this is important. So number one scenario is that let's say we are training a complex model and the training can take a long time. So it might take like one complete day or even a week, in case of complex kind of data and a lot of data, right? So what if the training fails after training for few hours or even days, so we are going to lose all the time, plus we will also lose money, because especially if we are running it on the cloud, then we are basically consuming all those resources at a money, right? So we do not want to start from scratch, right? So that is a point in there's a point in saving the weights of the model while training, because then at least we can restore the model from where it failed last time. So say for example, if you're saving the model say every half an hour, we can at least restore back to the last 30 minutes status actually. Okay, and also consider another scenario. Let's say we have trained our model, right? And after training we want to take it to some other server or to some other device, right? So for that we definitely need to export the model into device independent kind of a format so that we can take it to another device, right? Now there are two different flavors of dealing with the scenario of saving a model. So if you recall, a model has the weights and a computation, right? Now we have an option of saving only the weights. So if you are able to create the instance of a model once again, then we can just store the weights and restore the weights back into the model like a newly created model. Okay, and if we want to save the whole graph, that means if you want to take it to a place where we do not want to depend on the ability to create an instance of a model, then what we can do is we can bundle the model itself. We can save the model and the weights both, and then restore it back wherever we want it to have. Okay, so let's discuss a little bit of the code here. So what we are doing is we are discussing the first option here, that is creating a checkpoint. Okay, so just saving the weights is called as checkpoint. Okay, so what we have to do is we have to declare a path where we want to save, and then we have to create a checkpoint from our model. Okay, so we create a checkpoint, we create a path, and then we write a checkpoint to that particular path. Okay, so when we are writing a checkpoint to a path, what it is going to do is actually it is going to look at this particular model. It will take all the variables because as you can as we already know, it's easy to collect all the variables, right? Trainable variables, and then we can write it onto a storage device over here. Okay, so once it is written, we can also go to specific directory. So this is the path that we had, right? So we can go and list what is inside that particular directory. We can also see, let's say if there is a saved checkpoint, and if you know the path, we can go and also get a list of the variables into that particular path. Okay, now what about restoring it back? So what we have to do is we have to create a new instance of a model. So my sequential module in this particular case, and then we create a checkpoint once again which represents this particular model, and then we can restore the weights from this particular path, my checkpoint, into the model that we have declared here. Okay, and once it is restored, then we can call it as any model, like we can just say give it a tensor data, and we can basically the model will calculate a computation on those things. Okay, so that is the first option, checkpoint, where we are saving only the weights which are there in the model. And just to mention, actually, when we save a checkpoint, when we create a checkpoint, what we get is we get like two files. There is an index file and then there is a data file, right? So index file will store all the metadata, right? So, and the data file will store only the data. Okay, now the second option is to save weights and computation graph, right? So for that, what we do is we use the tf.saved model.save method, and we give it our model and the path where we want to save the model, and that's it. It is going to save, and once again we can go to this particular path and list all the files. So in this particular case, you can see that there is the saved underscore model.pb file. So it's a protocol buffer format file, right? And it is a device independent file, so we can go and restore this particular model onto any other device as well. Okay, so what we have to do here, we have to create a new model by using tf.saved underscore model.load, and we have to give this particular path where we had actually saved this particular model here. So for a checkpoint, we have checkpoint.write and checkpoint.restore methods, and for the save, we have this tf.saved model .save method, and then we have a load method here, right? And one thing to keep here in mind is that in case of a save and the load after that, we do not need the it's not necessary to have a Python interpreter, because we are using this tf.saved model.load. So this is a serialized model that we are loading over here. Okay, now let's also quickly discuss the different steps which are involved into the machine learning. So solving a machine learning problem usually consists of a few steps. So we have to get the data, then we might have to process the input data also. So there's this whole the science of processing the data, which is called as a data science, right? So raw data to the data which can be accepted by the training for the machine learning model, right? So once we have our data ready, then what we do is we build a model. So what we do is depending on the problem that we have had hand, we decide to build the model typically from different kind of layers. So we organize different layers and we create a model out of it. And once we have defined the model, what we do is we also need to use a loss function, right? And we also need to decide which optimizer we are going to run, and there might be little bit of data processing once again involved there for shuffling the data and also for creating the batches of the data and all. So once that is done, what we do is we run that data training data through a training loop, and for every batch we calculate a loss, and then we compare it with the actual predicted value, actual labels. The predicted value we compare with the actual labels, and we calculate the loss and feed it back to the back propagation. So we calculate gradients for that particular loss, and we use an optimizer usually to adjust the variables to fit the data, right? And then finally we go and evaluate our model. For that we usually keep a separate data reserved, right? So let's quickly go through these steps a little more in detail. So in this particular case we are taking a very simple example just to clearly see what those steps are. So here we are taking an example of a supervised learning, and in this particular case we are going to denote the input data as X and output data as Y, and the weight we are going to denote by true underscore W, true underscore B. So in this case we are basically trying to create a linear data set. So the relationship between X and Y is going to be linear. So what we are doing is actually we are creating or generating the X and Y into this particular case, which is related by a linear relationship. And what is that linear relationship? What we are going to do is we are going to take the X and we are going to multiply it with the weight, and then we are going to add a bias to it. And just to make sure that it is not totally kind of predictable, what we are doing is we are adding a noise to it. Okay, and we are generating this X as a simple vector here, and we are also generating some noise. Okay, and from the X and noise we are generating the Y here. So it is all synthetic data that we are taking here in this particular example. Okay, so once our data is ready, what we have to do is we have to create a model, right? So what we are doing in this particular case is we are subclassing this tf.module. We are calling it as a my model. It can be called anything, obviously, and we are creating these two tf variables, w and b, right? Because we want to have a linear relationship, right? Because this is the calculation that we are going to do, and which is going to require this X, right, and B. So that's what we are doing it into this particular step here, right? And we are setting this value as 5 and 0, right, which are different from our true weight and bias, because we want to basically see how does the training work, how the weight and bias is going to get adjusted during the training, right? So once again here what we are going to do is we are going to return here W into X plus bias. That is a simple calculation that we are doing here. Okay, and we create an instance of our model here. We can iterate whatever the variables into this particular module. We can also just do a quick check if everything is fine here or not by just using this assert here. Okay, so that is the step number 2. The key thing to remember, we extend our model from tf.module. We create this W and B within the init, and we put our calculation into the call method. Next step, we define a loss function, right? So in this particular case, since this is a linear regression problem, what we are doing is actually we are defining the loss function as tf dot reduce underscore mean tf dot square target y minus predicted y. Right? So what does it mean? So this is a true label, this is a predicted label, we square it, right? So that is the squared loss that we do. And why is it tf dot reduce mean? Because this actual the y and the predicted y, they could be the batches actually. So we compute a single loss value for an entire batch. So say for example, if you have 1000 pieces of data, and if you have split into like 32 pieces of data in a batch, then we are going to get a loss value for 32 data records, right? If we are using this particular loss function. Next step, we have to set up a training loop, right? So how does our training loop looks like? So this we have already created, right? Model we have created, and in the training loop what we do, we take this model, we take the input and we take the actual labels. Okay, so what we do here, we call a train method for each of the epoch that we have, and then we just append a weight value and a bias value at the end of each epoch here. And how many epochs we are going to run in this particular case? 10. Okay, so we are going to print the weight, bias and the current loss, right? So let's also take a look at this train method here, so which is there on the next slide here. So what we have here is train method, which is taken in model input the labels and a learning rate, and then we set up this tf.gradient tape here as t, and then we are calculating the loss under this context here, because we want to store this and do a back propagation on this. And once that step is done, we get the gradient of a current loss with respect to our model.w and model.bias variables. So this is what we get. But now this is a change, right? But we still haven't applied that change to the actual weights and the biases, right? So that is our next step. So we essentially do this assign underscore subtract on both of these, and this learning rate is coming into the picture here. So say for example is if this dw was 1 and this learning rate was 0.25, then we are saying that update the weights by 0.25. So by learning rate we can decide like how much update we want to do on the weights and the biases, right? Now if we run this whole loop for number of epochs, actually this is what we'll get, so this is our actual bias and this is our actual weight, true weight. Now if you remember, this true weight was 3 and the true bias was 2, and then we started with 5, right? For the weight. So that weight will converge throughout the epochs to the value of 3, and we started with 0 for the bias, and it will converge to the value of 2 throughout the epochs actually. And if you once again want to see where we did that, you can see it here. So we had initialized these weights and biases to 5 and 0, and our true weights and biases like 3 and 2 here, and then throughout the training it actually converged to the real. It started with something else and then it converged to this. Okay, so train step we already discussed. So that's all actually for this particular session, guys. In terms of the presentation, we are still going to see the notebook, so we'll go and see the notebooks and then we'll come back and discuss the summary. Okay, so let's take a look at the first notebook that we have, and that's about the modules and the layers, right? So as usual, we are going to start with importing the libraries. So in the meanwhile, while it is getting imported, what we'll do is this is the simple module. So we are just trying to see how the module can be created and how it can be used. So yeah, so the import is complete. So this is a simple module which is getting extended of or subclass, like I come from a Java world, so I have this habit of getting extended, saying extended, but in Python it's like subclassing. So simple module, two methods here, init and call. So here we are calling a trainable variable. So if we do not give anything, then it is a trainable variable, and we are naming it as train me, and we are creating a non-trainable variable by setting trainable equal to false, and we are naming it do not train me. Okay, so two variables, and in the calculation we are giving a very simple calculation wherein we are multiplying the variable by an input and then adding a non-trainable variable to it, right? So what are the values here? 5 and 5, right? Now we create a instance of this simple module, name it, and if we give it an input of 5, okay, so what's going to happen is going to multiply 5 with 5 plus add 5 to it. So that is what we get 30 over here. Okay, and why the shape is like no shape? Because it's a scalar, right? Now we had also discussed earlier that we can get a list of the variables, like trainable variables and the variables for a module, and that's what we are doing here. We have this instance of a simple module, and then we are executing these simple things here. I'm not sure if I executed this. Let me execute this part. Yeah, so that part is done, and then we will print this trainable variables and all the variables. Okay, so in the trainable variable we got this train me under train me 0, that is the first instance of the variable train me, and when we are listing all the variables like dot variables, we are getting this train me as well as do not train me, both the variables, right? Now we had seen this dense module, right? So this is also extending from the tf.module, and we discussed like the init method and the call method. This is the what you call the model that we had created, where we used this particular layer, and then we did a calculation on it, right? So let's run this part. So this part, so we created a layer here, and then yeah, we defined a layer rather, and then what we are going to do is we are going to create these two dense layers, and this is the calculation that we have. So input is going to pass through both of these layers, and then we are going to get our output, right? And let's do this calculation, right? So this is what we got. This is the tensor that we got, and shape is 1 by 2. Why 1 by 2? Because input was 1 by 3, and then we multiplied it with the 3 by 3, right? So 1 by 3 into 3 by 3 is going to be 1 by 3 again, and that 1 by 3 we are multiplying by 3 by 2, so we get 1 by 2. Okay, so that's the shape that we get here, 1 by 2. So if we do the submodules, right, what are we going to get, right? So what are the submodules? So submodules are the properties. So if you see here, this dense is a module, right? And we had assigned it to the property self.dense1 and self.dense2, these two tf.modules, right? So if we do this listing of the submodules, what you are going to get is actually two dense modules, right? And then this is how we can print all the variables. So we are iterating through the for loop, my model dot variable. So this is our first bias, 3 colon 3 colon. Why? Because the dense layer is 3 by 3, right? And this is the weight, so 3 by 3 weight that we saw. Now in the second case, since the outputs, there are two outputs, we get a bias shape as 2 comma and the weight shape as 3 by 2, okay, because there are two outputs. Now this is the flexible module that we had discussed earlier. So we can give input of any shape, and it's going to take the last dimension of the input as one of the the shape kind of variables over here. And then we do the same thing here, except that we are using the flexible module. So we are not giving the input features here, we are just giving the output features here, right? And where is it going to get the input features? The first parameter it's going to get from the input itself. It is going to get it from the x dot shape into bracket -1, right? So the same thing, but a little bit more flexibility here. Okay. Now comes how we can save these models. So let's say we have this, so we have created a model here, right? And we want to save that. So we declare this as a path, and then we assign a model to it, and then we write a checkpoint. So my checkpoint is written here. Now we can go and list that particular path, and we get this, right? So we have this data file and an index file here, right? We can also go and list what are the variables. So you can see that there is dense 1 bias and weight, and dense 2 bias and weight, and these are all the different dimensions of those variables as well. Okay. Now if you have to restore this, what we do is we create a sequential like instance of that particular model. We create a checkpoint from the model, and then we restore from the path. Okay, so we restore the weight into the new model, and then we basically call this new model with this particular data here, and these are the results that we are going to get, and they should be same as what we got earlier, right? Because these are the weights that we have saved. So just notice all the zeros here, and 2.74, 3.76 and 76 here, and that is what we are getting here, right? Same thing. Now we can go and save the model as well. We'll try out this save method also. So it is written now. So this has saved the weights as well as the graph now. So we can go and check this particular directory. So this directory we have purposely taken different from our checkpoint directory, so that we can see very clearly what is being saved. So we see that this is a protocol buffer file that we have, and if you change into the variables directory, it will give you the data files for those different variables as well. Okay, and now we can load back the model tf using the saved underscore model dot load method, and then we can call the new model with the data. And that's exactly the same thing, but the beauty of the saved model dot load is once we have the graph saved, then we can take this format anywhere else and load it back, and then just call that model. So it will you don't need to create a graph, right? Because the graph is already saved into it. The only thing is you cannot change the input method signatures if you are basically saving a model through this dot saved model, because the you have saved the graph, so it's not going to change when you load it, right? So that's pretty much about the notebooks that we wanted to see. And let's go towards the end of this particular, so let's go to the summary quickly. Yeah, so this is where our session 3 summary is. So we discussed that the model and layers a subclass from a common class tf.module, and tf.module has got this very nice property that it can nice feature which collects all the variables recursively, and it also collects the submodules automatically, right? And why this is useful? Because this really helps us when we want to save the weights or save the whole model, including the weights and the graph, right? Second concept, layer is used to encapsulate a type of the computation and associated weights, right? So we want to reuse a specific type of computation into a model, so it's a good idea to abstract it as a layer so that we can create our model, and we can actually create a model out of using multiple layers. And there could be many different type of layers, including dense layers, convolutional layers, pooling layers, and whatnot. Okay, multiple layers, and you can create your own layers also, right? And once the model the model is going to consist of layers, and it also has convenience method, because model is representing a complete network, artificial neural network, right? So it also needs to have convenience method for training a model, evaluating a model, and also getting predictions also. So usually we'll see at a later point in time when we look at the model classes in Keras, they will have all these convenience methods, right? Or you can create your own convenience methods also. So what we have to do is we have to subclass tf.module, and then we will have to provide all these different methods ourselves. Okay, now there are two variations of persisting a model. Now there are we discussed the scenarios why we want to persist the model, and if you want to save only the model weights, then we can use the checkpoint. If you want to save the complete model, we can use the .save method. Okay, and saving allows us to take the model to a different device altogetherly, and saving and checkpointing also allows us to restore back to a point where it might have failed, or at least nearby. So for example, if you are saying that if you are checkpointing every 30 minutes, we can at least restore back to the last 30 minutes. Okay, and we also talked about the machine learning steps, so getting and processing the input data, build model, and then as a part of the training we predict the target values using the model, we calculate the loss, and then we calculate the gradient of the loss, and then we update the weights using that gradient, right? So that was all for this particular session, guys. I hope you enjoyed all this. If you have any comments, please post your comments. I'll definitely take a look at them, and I'll be back with the next video pretty soon. So thank you so much once again for listening. Bye bye.